Here's another video for the lecture Intro PDE. In this video we present section 4.1, the complete section 4.1. So we begin with chapter 4. Chapter 4 considers the heat equation. So the heat equation looks like following: U dot minus Laplacian U is equal to 0. And this is the homogeneous, and the inhomogeneous is with right hand side. So U is the unknown function, and this goes from some open domain omega sitting in Rn cross R, yeah, to R, unknown function. And F is also a function from omega from Rn cross R to okay, and we have this function depends on x and t in Rn cross R or in omega. T is time, and U dot is of course, U dot of x and t is of course derivative with respect to time, as we already had. Yeah, and Laplacian U of x and t is of course divergence gradient with respect to x. Okay, so this is the heat equation, and the heat equation describes the diffusion process. Yeah, we already saw this. I in the characterization I already introduced this, and I explained the name comes from the diffusion, which levels inhomogeneities of temperature or chemical concentration or others. Now we the treatment of the heat equation is similar to the treatment of the Laplace equation. Yeah, and we try to make this analogy transparent. So we do more or less the same steps. Now in the first section we consider the fundamental solution. Okay, and we make a general ansatz. Yeah, first we make a general ansatz. We make the ansatz that U of x and t should be 1 divided by t some alpha, and then some function v, which depends only on this combination. Yeah, where v is a function. Okay, and if we make this ansatz now, then let's calculate the heat equation. Yeah, also here t, x is a vector in Rn, and t is a vector. Okay, here we restrict to the positive numbers. Yeah, otherwise this makes no sense. Okay, so this is first the ansatz, and now alpha and beta are real constants. And now we calculate. For this ansatz we calculate U dot of x and t minus Laplacian of U of x and t. So this gives, now what comes out? First, derivative with respect to time. Here we have two places. We have to take derivative at both places. First here, then we have minus alpha t to the power of minus alpha minus 1, yeah, if we take derivative, times v of y. And y is here just abbreviation. Okay, this is here the derivative. Now if we take here the derivative, then we get minus beta, and with respect to time, then we get also 1 power less, and this together, this again gives t to the power of minus alpha minus 1. And now the inner derivative is x divided by t to the t beta. So x divided by t to the power of beta and beta plus 1 by the derivative. So we get y, yeah, the plus 1 we already put here. And then, of course, we get divergence of v of y. Yeah, this is t derivative at this place. And then comes here x derivative of this place minus, and every x derivative gets such a factor. So we get t to the power of minus alpha minus 2 beta, because we twice take the derivative, and each time we get as an inner derivative t to the minus beta. So we get this factor here, and then we get just Laplacian of v of y, yeah, Laplacian with respect to y. Yeah, okay, so now we see, and this is should be 0, yeah, homogeneous heat equation. We first look for the homogeneous equation. And if we set beta equal 1/2, yeah, because then all these 3 factors are the same and they cancel. Yeah, then all these factors cancel. Okay, and so all these factors cancel. So it reduces to, yeah, and then and we multiply it by minus, yeah. So alpha times v of y plus beta times y times gradient of y plus Laplacian is 0. Okay, so this is now the next equation, alpha and so on. And now, like for Laplace equation, we make the assumption that v depends only on the absolute value, on the length. So w of the length. Okay, and then we call, yeah, the gradient. So this term is the same, w of r. Now we call r just divided by square root of t, yeah, because beta is 1/2. Okay, we have this alpha, this term here. Now what is with the gradient? Then we get plus. Now the gradient is v prime of r. And what factor we get here? Yeah, we get y square also the divergence is of course, yeah, also divergence y v of epsilon is the same as v prime of r times y divided by y absolute value. okay, if we multiply this out, then we just get absolute value. Yeah, so what do we get? Yeah, so sorry, here I should insert 1/2, yeah, because beta is 1/2. Okay, what we get here, yeah, here with this formula, what we get here, we get y squared. This is absolute value of y divided by y. So we get, in fact, we get r times and 1/2. Yeah, this 1/2 here. Okay, and Laplacian we already calculated. This is v double prime of r plus n minus 1 over r v prime of r. So we get this equation here. Yeah, this is now the equation after this. Now I claim if we set alpha equals to n over half, then we can integrate. Yeah, namely, the claim is r to the power of n minus 1 times w prime, and the same prime, plus 1/2 from r to the power of n v prime. No, sorry, v and the whole thing. Prime. Let's calculate. Let's do the calculation. Here, if we, r is of course the variable with which we take the prime. So we take prime. So this is n minus 1 times r n minus 2 v prime plus r to the power n minus 1 v double prime plus 1/2, and what is here this? This is n times r n minus 1 w plus r n times w prime. Okay, now let's write this r to the power of n minus 1. So what we get? We get n minus 1 over r v prime. Yeah, here this term. This is this term here. Sorry. Yeah, no. It's correct. Yeah, 1 power less. Okay, and then we get plus v double prime. So we see we indeed get this factor here. Yeah, we get this factor here. Now this factor here, if we put this out, we get plus n half w, and what we get here we get plus r half w prime. This is what we get. Now let's compare it here. We see this term is this term. This term here, no, sorry, this term is this term. This term is this term. This term is this term. And this term is indeed this term, yeah? If alpha is equal to 1/2. So we indeed get that this is 0. Yeah, so we may write for alpha n/2 the equation, so the derivative here is 0, so it's constant. Yeah, so this means r to the power n minus 1 times w prime plus 1 over r to power. This is some constant, and we call this constant A. Now, if W and W prime vanish at infinity, now because we want some decay for our solutions, then A is equal to 0. And then we can simplify. Yeah, so, and then we can simplify, because then this means, this means V prime is equal to R half W. Yeah, so this is then our solution. And of course, this we may integrate. Yeah, this tells us that ln W prime is equal R half. So exponential of, no, sorry, W also plus some constant, of course. Yeah, I should write plus some constant. And this gives W is exponential of R squared times some constant. Here I missed a minus, and here we get a fourth, minus fourth. Okay. And this constant we call B. Okay, now again, we take some special choice definition. Phi of xt equals, okay, we define it 1 over 4 pi t to the power of n half. This is some factor, and this is this factor t n over half, n over 2. Yeah, remember we made the Ansatz. Here. And alpha was n over 2. Yeah, so we get this factor. Okay. And now comes the exponential. Exponential of, and okay, minus x squared over 4t. Yeah, this is exactly what we had. Yeah, this is r squared. R squared is nothing than x squared over t. Okay, and so we get this factor is exactly this. Okay, and for so this is for positive t larger than 0, and 0 for t smaller or equal to 0. Yeah, this is not so important. Okay, this is just more or less a convention. Okay, this is fundamental solution. Of heat equation. And this function is similar to a mollifier on Rn. what does this mean? Yeah, now we prove lemma. Lemma, the integral is always 1. Yeah, and of course this function here, if we draw a picture, x, here 0, then it looks like this, and the smaller t becomes, this to as steeper becomes the function. This is for large t. No, sorry, for small t, and here for large t. For large t. But the important property is that the total integral is 1. Let's do the calculation. Total integral 1 over 4 pi t n half integral over Rn exponential of minus x squared over 4t dnx. Now we make a substitution. We make a substitution, and the substitution we make is that y is equal to x divided by 2. We make this substitution here. Of course, this means x is equal to y times 2 times square root of t. So dnx is equal to 2 square root of 2 to the power of n times dny. So here we see we already have exactly this factor in spite of the t. So this factor here, if we put it, so d power of x over 4t n half is dny. So this factor without the pi, this is, so we get, so this is equal, this is, here we continue, this is just some short calculation in between. So we have 1 over pi, still pi n over half, integral exponential minus y squared dny Rn. Okay, and this integral, now again calculation, exponential of minus y squared is of course exponential of minus y1 squared minus yn squared. And so this is a product. So this is nothing else but 1 over square root of pi integral minus y squared dy to the power of n. By this, since this is just a product over any component, and by Fubini. Here we used Fubini. And write this integral as an integral over all the components. Now, for n equals 2, maybe you know this trick, how to calculate this integral. For n equals 2, we can use polar coordinates. E to the minus y squared R2 d square y. Now we use polar coordinates. Yeah? The length of the unit circle is pi. So we get this is pi times integral. Now in polar coordinates, 0 to infinity. And then we have r e to the minus r squared dr. But this integral, we may calculate. This is pi, and here we have the function as an antiderivative of this function is of course here. If we take the antiderivative, sorry, I made a mistake. Yeah, the length of the unit circle, yeah, the length is 2 pi, of course. Okay. So this is 2 pi, and now here, antiderivative, this is minus, I claim, minus r squared. Yep. Because over 2. Yeah, because then the inner derivative is minus 2r, divided by 2 gives 2. Okay, this is the, and now 0 to infinity, and so this gives pi. This gives pi. Yeah, so, and now by this formula we see this shows that integral minus infinity plus infinity for e minus y squared dy is just equal to square root of pi. And so this indeed gives indeed the statement, yeah, so this is indeed 1. So 1 over square root of pi integral minus y squared dy to the power of n is just equal 1. Yeah? So we have proven this. Yeah, so we indeed have proven this, and this really shows that this behaves like a mollifier. Okay, and this again has a very similar consequence like in the Laplace equation. Yeah? This time we obtain not a solution of the boundary problem, but of the initial value problem. Let's see, what is the statement? Now we have this theory. We have a bounded continuous function on Rn, a real bounded continuous function. Yeah? CB means bounded and continuous. CB of Rn are bounded and continuous functions from Rn to R. Real functions under Rn. Okay, now the claim is, first of all, this is C infinity, then it solves the heat equation, and it extends continuously to the boundary, to T, the limit exists and is H. Okay, first of all, phi is smooth on Rn, and by the foregoing lemma, yeah, it's clearly that phi is smooth, and the boundedness, phi is of course positive. Yeah, phi of xt is positive and smooth, and the integral is 1. So by the boundedness, yeah, so integral over Rn of phi of xt is clearly well defined. Yeah? If it's bounded, yeah, in the absolute value, sorry, this is bounded Rn phi of xt, and now we estimate this by the supremum norm. dny, yeah, dnx, sorry, dnx. And now we can put this out, and this is, so it's really bounded. Yeah, and by the exponential decay, all derivatives, yeah, for all derivatives of phi, one has a similar estimate, yeah, due to the exponential decay, yeah, by the exponential decay. Yeah, yeah. So we say that this map, the map t going over to phi of dot t is a smooth map, yeah, from R plus to L1 of Rn. Yeah, and by continuity of the integral, continuity of the integral and linearity, yeah, we know this, and linearity, this implies that u of xt is indeed smooth. Yeah. Sorry, there's sorry, very important. Yeah. Here, of course, this should be convolution-like. So this means phi of, and then we write here y, and here also. Okay. Yeah, but this is estimate is true. Okay. And yeah, and the derivative with respect to x only depends on y. Okay, so we have indeed, this is smooth, yeah, so this is smooth. So this is a smooth function, and now we take the derivative since u solves heat equation, also not also u solves heat equation. Yeah, because here yeah, because the derivative with respect to here in this formula, x and t only depends on the derivatives of phi. Yeah. Okay, so by this formula we see this. Okay, and now y follows now. So we have the second point. Now we want to prove the third point. Yeah, why? What is the with the limit t going to 0? Yeah, and to estimate the limits t going to 0, yeah, we note the following. Yeah, for any epsilon, also for any epsilon larger than 0, and any x in a compact subset of Rn, there exists a delta such that this is smaller than epsilon for y in the delta ball around x, and there exists a t larger than 0 such that now the integral over Rn without this delta ball, phi yt dny, this is positive, is, now we may use this rescaling, scaling behavior, is equal to the integral over Rn minus the delta, the ball with delta square root of t, phi of y1 dny. Yeah, and this is of course smaller than epsilon, yeah, due to the exponential decay. Yeah, if t, sorry, I should say for all t is smaller than capital T. Yeah, you see, if t becomes very small, if this is smaller, then this ball is larger and this becomes smaller. Yeah. Okay, so clearly we just should insert capital T. Yeah, and we should choose capital T so small such that this ball here is large enough. Of course, if this ball goes to infinity, then this goes to 0. Yeah, so, okay, and this behavior, yeah, this is just again this rescaling which we used in the lemma before. Yeah, this is here, this rescaling. Yeah, if you please note that here we rescaled by 2 square root of t. Yeah, we rescaled, and this we use the same rescaling, and then we have this property. Yeah, so we have this property, and here we see if t goes to 0, then this ball becomes infinite, and then this goes to 0. So by choosing t large enough, this is always, we can make this arbitrarily small, and then this becomes arbitrarily small by t is making choosing small enough. Yeah, if t is small enough, then 1 over t is very large, and so on. So we can do this. And now we do, yeah, this is what we have done before already. Now we estimate u of xt minus h of x, absolute value. Yeah, for the same t. For the same t. Okay, this is of course smaller or equal to Rn, and now we divide it already in two things. Yeah, and Rn, okay, first we write phi of x minus y t h of y and minus h of x, yeah, dn y. Yeah, this is by dilemma. Since the integral here, the second term, this gives just this term here, yeah, and then absolute value. Okay, and then we can estimate this, of course, put the integral in, and to take two different parts. The ball, this around x with radius delta, phi of x minus y t, h of y minus h of x, absolute value dny, plus integral b of x. No, sorry, now we get the rest. Now we get the rest. N minus the ball of b phi of x minus yt. Okay, and on this set, far outside, there we estimate this. Okay, maybe I write this. dny. Okay, here we estimate this outside 2 times supremum now. And here it's smaller than epsilon by continuity. So if we insert this and use this as this is positive and integral is 1, we get epsilon plus, and here we get 2 epsilon. Yeah, so, and this is epsilon times 1 plus 2h infinity. So this can be made arbitrarily small, and this proves the claim. Yeah, this proves the theorem. Now this proves the theorem 4.3. So we have now constructed a solution of the initial value problem. Yeah? This shows that u of xt solves the initial value problem. U dot minus is 0 on Rn cross R plus, and u is equal to h, no, sorry, I should write u of x0 is equal to h of x for all x in Rn. Okay, now we finished this. This finished this section 4.1. So what we have done today, we introduced the heat equation, homogeneous and inhomogeneous heat equation. Then we made an ansatz. We constructed a solution. With some special choice of the constants, we obtained a fundamental solution, and then we saw that with this fundamental solution behaves like a mollifier, is very similar to a mollifier, and then we proved that with this solution we obtain a solution of the initial value problem. Thank you.